contained in a finitely. Right, I mean, it's finitely managed others. Maybe it's not closed under Q, but certainly contained a finitely generated vector space, finitely dimensional vector space. Okay, so now I want to say that it means that if this LD of gamma is contained in a finite dimensional vector space, then LD of gamma, let's say also the dimension is less than or equal to what I denoted R, number of generators, right? Because that's the number of generators of gamma. So it means that this LD of gamma satisfies a linear ODE of order R. Less than or equal to R. Now here we're using some kind of intuition from differential equations, right? What we have is a finite dimensional vector space over Q. Q are constants. So think about just classical differential equations. You have, I don't know, R functions, so you have some collection, vector space of functions of a given dimension. Then you can write a differential equation which is kind of killing all of these functions, right? You can do it using Vronskyans. If you have, if these generators are, I don't know, G1 up to Gn, then you take kind of the Vronskyan of G1 up to Gn and then some kind of indeterminate function. You expand the Vronsky, you'll get a linear ODE of this order, and it will kill all of these functions. So it means that we've now managed to write this, it's still not gamma, but LD of gamma kind of embedded into the kernel of some differential equation. That's where differential equations come from. And then it's very easy to kind of, we pull back by gamma, pull back by this logarithmic derivative. Then gamma will also be contained in some kind of, gamma will satisfy some differential equation of order, maybe R plus 1 now. I don't want to be specific about the numbers, but well, I mean, if the logarithmic derivative of gamma satisfies the equation, then kind of just plug in. So we know that dy divided by y satisfies some differential equation. So just plug in this dy divided by y into that equation, you get an equation that y satisfies, maybe of one order higher, because this involves already dy. But if you just plug it in, you will get some equation. So I don't want to be stickler about this number. If it's R plus 1, maybe this one was R minus 1. Never mind. So the point is, in this way we got that gamma satisfies some system of differential equations. That's where I wanted to go. Okay, so now what to do? I want to apply the theorem, right? Let me call this, okay, so gamma satisfies some system of differential equations.
Before you do it, is there any chance you could do some really stupid example? Like if I take n equal to 1 and just take the multiplicative group and think about things for the moment as rational functions, and take r equal to 1 and look at the group generated by, say, t. So where t is something with derivative 1. So my group is,
so let's take
integer powers
just
t.
C star.
Yeah.
And you just want the group generated by gamma will be, I don't know, f.
Sure.
Yeah. Group generated by one kind of function.
Yeah. And let's say that the derivative of f is 1.
Say that the derivative of f is
1.
Derivative of is 1?
Yeah.
Well, then it's very easy to give an equation satisfied by f, right? It will be df is equal to 1.
No, but, sure, but would that equation, but I think are you giving an equation satisfied by the generators or by all elements of gamma? You're saying gamma satisfies the differential equation.
Yes, I'm saying gamma satisfies the differential equation.
So f squared will not satisfy.
Yeah, you're right. So let's look what would be so we need to take logarithmic derivative of f. So we'll do logarithmic derivative of f. This will be 1 over f.
Yeah.
Now we should find a differential equation satisfied by this 1 over f. So probably it will be 1 over f prime is equal to whatever it's equal to.
Sure, negative h squared.
And right, so now we'll get to some equation, like 1 over f prime is equal to
negative 1 over
something.
negative 1 over f squared.
Yeah, but it doesn't matter. I mean, any some kind of constant. So so this is an equation satisfied by the logarithmic derivative.
Right. Okay, thank you.
Now you can, from here it's clear?
I think so.
Well, I think the issue really is if you have two generators, because then you have different equations.
You have two generators, so we'll have, each of them will have a logarithmic derivative. You'll get some two functions. Never mind, let's call them h1, h2. Now you want to write a linear equation whose solutions are containing kind of h1 and h2. So the only question is, can you write a linear equation which is satisfied by h1 and also satisfied by h2? Then, I mean, of course you can, using Wronskian, for example. I mean, for any tuple of functions, you can write a linear operator that is satisfied by these functions. There's various ways to do it. For example, with Wronskian. Okay, so I want to say even a bit more than I said there. So I said that gamma will satisfy something equation of a given order. So that is gamma is a subset of some G, which is differential algebraic. So G is kind of the zero locus of this equation that I constructed there, differential algebraic, and in fact I'll add the word here group. So this G in fact will be a group. So again, this is because I started with a linear ODE for the logarithmic derivative. So solutions of this linear ODE, they were a Q vector space. When you pull back by this logarithmic derivative, because this is closed under addition, this will be closed under multiplication. Again, now it's kind of going the other way with the logarithmic derivative. Logarithmic derivative, if the logarithmic derivatives are closed under plus, then kind of the original functions are closed under times. So we have managed to take this group, it's a group, but definitely not differential algebraic, it's kind of highly discrete, and we embedded it into a slightly larger group, or maybe much larger group, which is differential algebraic and still a group. So, and this is maybe the kind of the key philosophical approach that Bouillon started. Like, you want to work with some group which is complicated and discrete. First you extend your structure, so you look at, let's say, a differentially closed field. Then you extend your group. So you started with some group which is complicated. Find a bigger group which is supposed to still capture some traces of the original group. So kind of supposedly maybe studying this group, we could understand something about this group. That's the hope. That's the motivation. So, okay, now comes some magic. So I'll also say that dimension of G is finite. This is not a magic. This is just because solution of this operator that I constructed was...
What kind of dimension are you talking about now?
So this is dimension as a differential algebraic group. Okay. So, you know, if you take a generic point and you consider a derivative, what is transcendence degree, for example. So it will be same r plus 1, right? Because I just started with something that has just a linear space of solutions, dimension r, and then I pulled back by this logarithmic derivative. Mm-hmm. So, okay, now comes the magic. So, I will not expose the magic. So model theory gives that if you have a group satisfying this rule, so I mean if you have a finite dimensional group and you have the x satisfying the rule that I started with, so an x such that for any two positive dimensional varieties the sum is not contained in x, then x intersect G. Taking out this x cube r, is finite. Okay, so we wanted to study this thing with gamma, right? The original question was to find x intersect gamma and throw out the algebraic points. So what this kind of, first we extended even for g, which is, I mean, it will be much bigger, this thing, because g is bigger than gamma, but still it will be finite. And here you need to use some tools. So Bouillon proves this kind of results using his kind of theory of differential algebra plus some complex analysis. Hrushevsky and Pillai prove it using some stability theory and model theory. But, I mean, I will not discuss how to get this. But then, so let's say we know this. Then, this Hrushevsky and Pillai estimate automatically gives a bound. Right? Because now this thing is already the kind of thing that Hrushevsky and Pillai consider. X is just an algebraic variety. G is something defined by differential equations. Okay, we need to throw something out here. Again, I said we can throw out, we can kind of consider Zariski open subset. So just to throw out this thing. And then really we have some system that has finitely many solutions, and then we count the solutions. So kind of after you have this, then this step is just to apply Hrushevsky-Pillai. Okay, so now I want to kind of say what happens with when you apply my theorem instead, and it's kind of, it was my first motivation to prove this theorem. So the theorem, so basically up to here nothing changes, right? I mean, we are, all we did here is kind of, it's a qualitative analysis of the situation. It's not about counting. Counting really happens on this last line when you apply the Hrushevsky-Pillai result. So instead you can go up to here and then count with my result. The point is that, you know, you have here, for example, when you do the estimate, you really do the estimate by degrees of equation. So we wrote some equation here, kind of for this LD gamma. It's quite easy to estimate all the degrees. It's some Vronsky, you just count degrees. And then when you pull back by gamma, again, so you get kind of a very explicit system of equations, so you can just plug it into the theorem and see what you get. So now in the same context of theorem 1, so in this theorem 1, I work in the same context, but suppose x is cut out by equations so I want to do it by equations with polytope delta. Then this number, I erased the result already, but kind of the same number as we were bounding before, this intersection with gamma, same as in theorem 1, is less than or equal to some constant, C tilde, depending on n and r, times the volume of delta. So it's kind of the same story. Again, just because you plug things in, but there is a delicate point here that I want to stress. So notice that this x, it's an algebraic set. So this delta that we're talking about here, it's kind of in Rn. Right?
Yes.
Now we have two different ambient dimensions that we should think about. There's this Rn, it's the original ambient dimension, and then there is also what I denoted S before. It's n times r plus 1, right? Because these are differential equations, right? So actually they're differential equations of degree r or r plus 1. So really the ambient dimension, if you want to think about the system of differential equations, is n times r plus 1. Now, here I'm saying only kind of a delta in R to the n because it's the delta of x, right? It's not the delta of the conditions I get in the end. It's only the delta that defines this x, and x is an algebraic set. So the point is that when you look at this thing, it consists of two different parts. There is x. X is defined by equations of
0.
there is the x, which defines by equations of order 0, yes?
Yeah.
And then there is g. But g doesn't depend on x. Right? G, it depends kind of on the number of generators. It depends on the generators. The degrees of g depends on the number of generators. So let's say we fix some generators, then we already got some g. This g will have a certain order in all the variables, including the derivatives. Now let's say we take more and more complicated x. So my x will grow in degrees. So when I'm doing this, I'm fixing the degrees in all of the variables except for the algebraic variables. Right? When you take more and more complicated x, you increase the degree with the algebraic variables. You don't do anything to the degree with the non-algebraic variables. That's why my estimate will be, let's say we took an x which is defined by equations of degree d. Then my estimate will look like d to the n, not d to the n times r.
Right.
Okay, in Khushevsky and Pillai it was d to the 2 to the n times r, because they don't differentiate the different variables. When you do it with Newton polytopes, you can say, well, I'm allowing a degree up to a certain d in the first variables, in the algebraic variables, but I'm allowing a much smaller degree in the rest of the variables, because it only depends on the g, it doesn't increase when I change my x. So that's why you can get more tight estimates in this way, because you're just playing on the different variables. And it often happens it's a useful thing to have when you apply this philosophy, because this is how this philosophy often works out. So first let's say you want to study some lattice. So you embed the lattice in some algebraic group. This group is fixed now. And now when you consider how it interacts with different algebraic sets, then you're really increasing degrees only in a certain subset of the variable. So you can get better estimates if you think about these mixed degrees, where you fix different degree for each variable. That's why I did it just for Newton polytopes to begin with, instead of, if I did just for degrees, if I just stated the result if all my polynomials have degree less than d, then the bound is d to the s. Then I couldn't take advantage of this different asymptotics that my degrees take here, and I think different sets of variables. So I want to point out one corollary of this, which is maybe the reason that Khushevsky and Pillai got involved in it. So Khushevsky and Pillai improved the result of Bouillon, which answered the question of Bombieri. So there's a question of Bombieri. The question is as follows. We have f, which is in qx, y. So just q bar f y. We have an algebraic curve defined over algebraic numbers. Let's say degree of f is equal to some d. Okay, and we'll also assume that if we look at f equal to 0, in the torus, so I'm thinking about it in two variables, so I'm thinking about it in C star 2 is not a translate I also say that f is irreducible, just to simplify the presentation. So I just have an irreducible curve defined over Q, and I assume that this is not a translate of a torus. If it's not, it doesn't just define some subtorus of the torus.
Oh.
Okay, so in this case, this condition of Khushevsky-Pillai's theorem automatically holds. The Khushevsky-Pillai theorem said that if you have for any two positive dimensional subvarieties, the sum should not be contained kind of in the same variety. But here, it's already a curve. Kind of the zeros of f are a curve. So a positive dimensional subvariety of a curve, it can only be a curve itself. So kind of the only thing that can happen is if the curve plus itself is just equal to itself. So only if really it's just a torus. So in this very simple setting, that annoying technical condition of Warshawski and Pillai, it becomes nothing. And then the question was to we have this, and we also have this gamma in this. I'll show how Bombieri stated it slightly differently than we did before. We take gamma now, which is in C star, not in C star 2, again with R generators. And then the question is, so estimate the number of points xy in gamma square. So we are looking kind of a solution such that each of the coordinates is in gamma. So xy in gamma square such that fxy is equal to 0 and x is not in q bar. So it's similar to what we considered before, slightly more restrictive. So now we just fix some kind of subset of C star generated by R elements. We're asking kind of in this space gamma 2, how many solutions can there be for f? Again, not algebraic solution. So we want x to be, x should be not in Q bar, same as before. We don't consider algebraic solutions. And then Guillaume, he gave the first bound for this question. The bound was bad. So it was something like d and then factorial to the d. This factorial to the d means iterated factorial.
Yeah.
Iterated factorial. So a very large number, but still it's not even clear to begin with that this number is finite. It's a finite problem, and I think that Bombieri knew that it's finite, and he asked for if there is an effective method. So this was the first effective one. And then with this Warshawski-Pillai, they got a much better bound, which is that this number is less than or equal to d to the power something like r times 2 to the r. Again, I'm cheating a bit. Something like that. So roughly it's d to the, now the dimension is just 2, right? I mean, we are kind of c star to the 2, working two variables. So kind of the r comes into the second exponent, right? So we get 2 to the r. And if you apply my result, then we can get, so finally that the number is less than some constant depending on r, but in a single exponential. So okay, I write it times d squared. And this CR is just a single exponent in R. I won't write exactly what it is. It's not e to the, I mean, when I write x bar, I don't mean e to the r. I mean some exponential expression in R. Maybe it's something like 2 to the r square or something. But again, the improvement is in these two directions. One is that you get single exponent in R instead of double exponent in R. The other is that with d, you really get kind of the best that you could expect. You get just d squared as if it was, I don't know, just Bezout theorem, kind of two equations in C2, then you get d squared. And again, the reason that we get d squared here and not something involving R is exactly this thing I talked about before. So now I'm increasing the d, I'm only increasing the degrees in these original variables x and y. I'm not increasing any other degrees. So that's why in my result, asymptotic with D will be like D square, and then there will be some asymptotic depending on R. Right? I mean, because actually it's equations in R, of order R, they're other variables, but just they're not growing, they're fixed with R. So that's why we have some constant here depending on R. And nothing is doubly exponential. I mean, this result is single exponential, so all the constants are always single exponential. Okay, since that I'm out of time without talking about the proof, but for next time.
Maybe given
Questions?
the time, we should save the questions for afternoon, or unless there are very quick questions.
Are we meeting it too?
Are we meeting it too? I cannot,
But if possible.
but we're always happy to question speakers.
I'm here. I mean, you can ask questions whenever. Here,
Excellent.
later.
Meet it too, yeah.
Yeah, so maybe let's go have lunch.
Yeah.